Find the inverse of a 3 by 3 matrix. Now there's two ways we could do this, right? The first way, just like with a 2 by 2 matrix, we could use a determinant and some algebraic properties to work out the inverse of a 3 by 3 matrix. But it's quite long-winded and it's a long thing to do. So there's another way we can do it using the augmented matrix, which allows us to find the inverse just using elementary row operations. And the easiest way to see this is with a simple example. So our example says, find the inverse of A being this matrix. So we set up a giant augmented matrix like so. We've got our matrix A on the left, 1, 1, 1, 2, minus 3, minus 1, 5, 2, 3. And we put the identity matrix on the right-hand side. 1, 0, 0, 0, 1, 0, 0, 0, 1. And the goal is to use elementary row operations so that the identity matrix appears here, and whatever will then end up on the right-hand side will be the inverse of the matrix. I'll show you a small justification for that at the end of the video, so stay tuned for that. So let's start with our elementary row operations using Gaussian Elimination or Gaussian Jordan Elimination. We're going to try and create zeros in these places to start with. We're going to say row 3 becomes row 3 minus 5 row 1. So 5 minus 5 is 0. 2 minus 5 is minus 3. 3 minus 5 is minus 2. And then the right hand side, 0 minus 5, 0 minus 0, and 1 minus 0. So now we can't get a 0 here because it will affect this 0. So the next one we're going to try and get a 0 for is here in row 2. So row 2 is going to become row 2 minus 2 row 1. And there's no right or wrong way to do this. As long as you're building it up and getting an identity matrix, then you're fine. It just takes a bit of trial and error and puzzling. So let's do that one. So we've got 1, 1, 1, 1, 0, 0. Then row 2 is changing. So 2 minus 2 is 0. Minus 3 take away 2 is minus 5. Minus 1 take away 2 is minus 3. 0 take away 2 is minus 2. 1 take away 0 is 1. 0 take away 0 is 0. And the third row is unchanged. So now that we've got a 0 here and here, we can get a 0 here, because by adding a multiple of those, these will still stay as 0. So row 3 is just going to become row 3 minus 3/5 of row 2. Why 3/5? Well, 3/5 of 5 is 3, so minus 3 minus minus 3 is 0. We've got 1, 1, 1, 1, 0, 0, 0 minus 5 minus 3 minus 2, 1, 0, 0, 0. So that's minus 1/5. Minus 5 take away 3/5 of minus 2. That gives us minus 19 over 5. Feel free to check that out yourself. 0 take away 3/5 of 1 is minus 3/5. And 1 take away 0 is just 1. So we've now started to build our matrix up. Remember, we're trying to make this look like the identity matrix, making row 3 become a multiple itself. Row 3 becomes minus 5, row 3. So we've got 1, 1, 1, 1, 0, 0 still. 0 minus 5 minus 3 minus 2, 1, 0. And we've got 0, 0, 1, 19, 3, and minus 5. Excellent, our fractions are gone. How good, how glad do we feel at that point? Let's deal with row 2 and get a 0 in this position. So row 2 is just going to be row 2 plus 3 row 3. 1, 1, 1, 1, 0, 0, and 0, minus 5 add 0, minus 3 add 3, which is 0, minus 2 and 3 times 19, 55. 1 plus 3 times 3 is 10, and 0 plus 3 times minus 5 is minus 15. And we've still got our bottom row. Might as well make a 1 in this position just by dividing this whole thing by minus 5. So row 2 becomes minus a fifth of row 2. 1, 1, 1, 1, 0, 0, 0, 1, 0, minus 11, minus 2, and 3. We're almost there. Only got this last top row to do. We've already got a 1 in the correct position, so we just need to try and get some zeros dropping out here. So the first thing we might as well do is do row 1 minus row 2. So that gives us 1, 0, 1. 1 minus minus 11 is 12. 0 minus minus 2 is 2. And 0 minus 3 is minus 3. So one last operation to go. We need a 0 in this position. So we may as well, since we've already got zeros here, adding a multiple of row 3 won't change anything. So we might as well do row 1 minus row 3. So we get 1, 0, 0. 12 minus 19 is minus 7. 2 minus 3 is minus 1. Minus 3 add 5 is 2. Then we've got the rest already done. So you can see we've ended up with the identity matrix on this side and some new matrix on this side. This is now the identity matrix, and this matrix will now be the inverse. So to be clear, the inverse of A is this new matrix, minus 7, minus 1, 2, minus 11, minus 2, 3, 19, 3, and minus 5. So why does this work? Well, if we find the inverse of a 3 over 3 matrix, it involves row reducing this giant augmented matrix. So we've got A being our matrix augmented with I, so that it becomes I augmented by some matrix B, and B will be the inverse of A. And how you can think of it is like this. If we're taking our matrix A times some vector x equal to some vector p, that's the same as taking the matrix A augmented with p. Now if we times both of the sides of this equation by the inverse of A, we get A inverse AX equals A inverse P. But that gives you the identity on this side times X equals the inverse of A times P. Now in augmented form, that means we've got the identity augmented by A inverse P. Now if we choose the vector P to be each of the 3 columns of the identity matrix, then P essentially picks out the columns of the inverse of A. So the calculations is more convenient, of course, if we start with the whole identity matrix instead of separating it out into separate columns, which is why we did that in the previous example. Hopefully that gives you some sort of justification for this. One last thing, some properties you should be aware of, and feel free to try and prove these yourself. If we do AB inverse, you get B inverse, A inverse. It's the same thing. So obviously we're switching the order here. K times A and then inversed is the same as doing 1 over K times the inverse of A. If we take the transpose of A and try and invert it, we can also instead just do the inverse of A transposed. And last but not least, the determinant of the inverse of A is the same as 1 divided by the determinant of A. These are important algebraic properties that are useful when proving certain things with matrices. Take care, stay safe, and goodbye.